have been looking at the Bragg condition. A few issues with Bragg conditions still left undiscussed. I left this diagram for you to analyze, but I thought that maybe I should explain it a bit more. Other than that, this new diagram I have put in, this new diagram will tell you that if you consider this, let us say, is the plane from which the diffraction or the reflection of the incoming radiation is giving us the diffracted beam. Now, essentially the diffraction from all practical points of view under the Bragg's law, we consider it as a reflection. That means the angle of incidence and the angle of diffraction, they are one and the same. And because of the fact that this distance AB, in fact AB will represent now the wave front associated with the incoming, that is the incident radiation, and CD will represent the wave front which is going out after the scattering. So, that would mean that this angle is 90 degrees and that angle is 90 degrees. So, which essentially tells us that if you take any point on the plane, take any plane and take any point on the plane, the diffraction condition is still the same. That means, if you see this angle ACB and the angle CAD, these two angles are one and the same, which happens to be equal to theta. And because these two angles are equal to theta by construction, it means that all these points, any point in this plane will scatter with the same phase. So, if you assume that there are different kinds of atoms in different parts of a given phase, all those atoms will scatter in phase. Suppose you consider this as the plane passing through the origin, and at along different directions, different distances, different atoms lie on that particular plane. As far as the phase associated with this plane is concerned, it is always 0, because it is passing through the origin. And if atoms sit on this particular plane, the phase that is scattered by these atoms will also be 0. So, this is a very important point, that they scatter with the same phase if you consider any point on the plane. So, which means to say that in a given plane, any plane for that matter, it need not pass through the origin, any plane there may be several atoms sitting. This is again taking you back to the bread analogy, where we take a slice out, there may be several pieces of different things which we have added in the piece of bread, and therefore, different electron densities associated with different atoms may coincide with that particular plane. All these now will scatter with a single phase, and this is a very important phenomena, because then we need not have to worry about what are the contents of that plane as far as phase determination is concerned. Suppose in this particular plane there is a carbon, there is a nitrogen, there is a bromine, there is a iodine and things like that, which parts of it of course. And all these electron density therefore, will all scatter with the same phase phi associated with the plane. So, this factor will help us in actually determining the structural details in a later point. So, what we have to take home, the take home lesson from this particular diagram is that the scattering is associated with the same phase, and that particular phase angle is now with respect to the plane. So, suppose these atoms are not in this plane and somewhere else, the contribution of this plane to the scattering will still have the same phase. So, the phase angle is therefore a property associated with the plane, and the contents of the plane, now whatever be the contents, the phase angle will still be the same. And this is the phenomena which in fact will come in handy when we determine the structure later date. Now, regarding this diagram, which we already discussed a bit in the last class, we see that the wave front again here in this case is shown as AP. So, this difference this defines the incoming unit vector S naught, and this is the vector S, which is the scattering vector. And what is represented here are the two different planes separated by a distance d of HKL. So, whatever are the atoms on this plane, they will all scatter in phase, whatever are the atoms in this plane, they will scatter with that particular phase. And if we consider the first plane which is out of the origin, suppose A is the origin position, then the first plane out of the origin will scatter with a with a path difference of lambda and therefore a phase difference of pi. So, that defines in fact the Bragg's law, that is because of the fact that this little geometry construction will tell us. So, if you look at AP and AQ, these AP and AQ are plane wave fronts. The path difference is that if you consider this particular wave and the second wave which is going up here, the path difference will be additional PB plus BQ. So, the additional path the second wave is travelling is PB plus BQ. Now, the value of PB plus BQ can be calculated as based on this diagram, because this is the angle of incidence, this is the angle of diffraction, and therefore, this is the angle of incidence and this is the angle of diffraction. These two triangles are similar triangles. So, APB and ABQ are similar triangles. The property of the similar triangle is that the external angle will be equal to the internal angle. So, these two angles will also be theta, and therefore, this will be one side 1 d sin theta, the other side another d sin theta. So, it accounts for 2 d sin theta. So, PB is d sin theta, BQ is also d sin theta. So, PB plus BQ is 2 d sin theta. So, in order for the reinforcement to occur, in order these two waves now overlap with each other, this should be a whole number. In other words, if the diffraction has to take place, these two have to be a whole number of n, number of wavelengths. So, the first one will be 1 lambda, the second one plane will be 2 lambda, third plane will be 3 lambda and so on. So, therefore, they satisfy this equation 2 d sin theta is equal to n lambda. So, you get the Bragg's equation 2 d sin theta is equal to n lambda. That is the condition which is derived from this particular diagram. So, therefore, these two diagrams tell us two major things. One is that when there are points, any point on this given plane will always scatter in the same phase, irrespective of where the point is on that particular plane. And when we consider parallel planes like this, which are separated at a distance of d of HKL, we get the condition that 2 d sin theta is n lambda, and that is the way in which the Bragg's law appears. To see what is the value, what is the role of this n, which is referred to as the order of the reflection. We have already discussed this, but we will again look at it from the point of view of how the angle changes with respect to the variation in the values of HK and L. Suppose this HKL is 210, the value of 210, if you consider the value of 2 times D420, where you have now taken 2H, 2K, and of course, you can call it 2L, but it is 0, 3 times D630, that is the 3 times. So, we therefore see that the value of D210, this is the value of D210, the spacing between these two planes is twice 2 times that of the plane distance between these two, and 3 times that of the distance between these two. And therefore, D210 is equal to 2 times D420 equals 3 times 630. So, as a consequence, what will happen to the sin theta value? The sin theta value, which is again following this formula 2 d sin theta n lambda, we see that sin theta 210 will be half that of sin theta 420, as is illustrated here. This is the theta angle, this is the theta angle, the angle of the between the incident and the diffracted. So, this is the incident angle theta, this is the diffracted angle theta. So, the angle between these two therefore will be 2 theta. So, this I and D now come at a certain angle sin theta 210. This now becomes 1/2 of that angle, and this now becomes 1/3 of that angle, and if we consider the 4th order reflection, it will be 1/4 of that angle. So, the order of the reflection therefore tells us what should be the angle that is at which the diffraction occurs. So, at which the incident ray comes and falls on the plane, and these are of course all parallel set of planes. So, from the X-ray diffraction point of view, and when we do an X-ray measurement, even though this is a general equation 2 d sin theta is n lambda, your n value can be different from each other when the diffraction spots come. So, when you have the reciprocal lattice points, these reciprocal lattice points can have different values of n. So, therefore, we get 2 d sin theta equals lambda for the first case, 2 d sin theta equals 2 times lambda, 2 d sin theta 3 times lambda, and so on. So, as a result, the position of individual reciprocal lattice points we will already put a formula which is 2d sin theta equals lambda. So, the order of the reflections will appear in a diffraction geometry in such a way that each of them will represent a separate position for the reciprocal lattice point, because this now will occur at this point, this will occur at that point, that will occur at that point, and that depends upon the angle between the incident and the diffracted rays, which is given in terms of these values. So, therefore, in general 2d sin theta is n lambda, but for all practical purposes in a diffraction experiment we take it n equals 1. So, we therefore get 2d sin theta equals lambda, which is what we will be using in the entire analysis associated with the reciprocal lattice. Now, we discussed a little bit of this diagram yesterday, but we will redo that in the sense that we have to now consider the relationship between the direct space and the crystal structure and the reciprocal space and the diffraction pattern. Now, this is a factor which is of crucial importance, because what we will observe from a diffraction experiment are these. What we will observe from a diffraction experiment are these reciprocal lattice points. So, when you put a crystal in the X-ray beam and diffraction occurs, you will get spots depending upon the quality of the single crystal, and these particular spots will tell us the points of the reciprocal space lattice. So, this therefore defines the reciprocal lattice. Now, what is the relationship between the direct lattice, which is up here, which is our unit cell defined it. Suppose you take this as a 2-dimensional crystal, you see that this is represented by the A value and this is represented by the B value. Therefore, this red square here will be the unit cell. Now, this unit cell repeats itself because it is a crystal in both the directions. So, this therefore now defines the crystal space. So, this is the lattice representing our crystal. So, the angle between A and B, which is gamma, will also decide the orientation of these A and B with respect to each other. So, in other words, this angle which is here could be gamma. So, that is because of the fact that these two are identical. I can show the gamma here, I can show gamma here, I can show gamma here, I can also show it here. So, this you know already. So, we have therefore a direct space and a corresponding crystal structure. So, the atoms are all lying here in this part of the diagram. So, they are here, 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 wherever, depending upon where the atom wants to be and where the molecular structure develops or the ionic structure develops and so on. The atoms are connected to each other, as we discussed yesterday. The scattering is done basically by the atoms, that means the electrons associated with the atoms. So, X-rays when they fall on this crystal, they will be diffracting based on where the electron density is found. So, the larger is the electron density, the more intense will be the diffracted spot. But the observations which we are going to make is with respect to the individual planes which are defined in the direct space. Now, what are these individual planes we define in the direct space? We will define, for example, a plane which is now going through the origin, and therefore, as we discussed, all the atoms which may lie on this will scatter in phase, in the same phase, they scatter with the same phase, they 1 is 0, and in that particular case phi will be 0, the phase angle will be 0. The plane which is coming out from here, we can consider several planes which come out from here, but what we have done is a set of parallel planes. So, we have drawn here the plane which is now represented by a line, because we have shown it in 2 dimensions, the plane is perpendicular to us. So, if we now consider this particular plane in 2 dimensions, it can be represented as 1, 2. Now, why 1, 2? Because we see that this blue line intersects this red unit cell at 1 unit along A and half unit along B. So, we said already that the indexing is done in such a way that if there is a cut of half, it will be actually 2 in terms of the identification. So, therefore, D is 1, 2. Go back to the bread analogy where we took the central slice and said it is at half position along A, but that would mean that it is a 2, 0, 0 reflection if we are considering the reflections along the A direction. So, the same analogy brings up here the value which is the distance, the black line here indicates the distance here indicates the position of D12. This is the length of D12, that is the value of the D value of 1 2, 1 2 being the plane which we are representing here. So, if this is the 1 2 plane, the next parallel plane will be what? The next parallel plane will be 2 and 1. So, this is 2 and 1, this is 1 and 2, and this will be 2 and 1, and this will be 3 and find out. Okay, now, we have gone into the next unit cell up here, if you consider the intersection, but it is a parallel plane to this one. So, all parallel lines with respect to 1 2. So, in 1 2, 1 along the A direction and 2 along the B direction, that becomes half of that. So, this will therefore be 1 3, right, 2 3, 3 3 sorry. See, 1 comma 2 is up here, the parallel plane to that will be what? This will be 2 comma 1, the next parallel plane will be 3 something. Now, if we consider this as 1, this will be now 3 by 2, 1 and a half, and therefore, this intersection point will be what? So, if this is 3, that will be what? Find out, and then you see that these are now a set of parallel planes. Okay, this set of parallel planes, let us go further. Each set of parallel planes are represented by this vector. In this case, the plane 1 2 is represented by D 1 2, the distance of 1 2. Now, the corresponding reciprocal lattice vectors will occur with respect to A 1 over A, this is the vector direction, 1 over A vector direction represents A star, and 1 over B vector direction represents B star. This is now the value gamma, and therefore, this will be the value gamma star to define the 0 1 and the 1 0. So, the reciprocal lattice points are now represented as 1 0 and 0 1 with respect to the reciprocal lattice, and this angle will be gamma star is 180 minus gamma, where gamma is this angle. Suppose this angle is exactly 90 degrees, this will also be 90 degrees. So, A will be 1 over A, B will be 1 over B. Here also, as far as vector directions are concerned, it will be 1 over A, 1 over B. So, this therefore, now represents the A star B star axis, and this is 1 0 in this direction and 0 1 this direction. So, if we now take all the reciprocal lattice points along the B axis, B star axis, we will have 0 1, 0 2, 0 3 and so on, and the corresponding values in the A direction are 1 0, 2 0, 3 0, 4 0. We will therefore get the intersection of 1 and 1 as 1 1, then 1 and 2 as 2 1 and so on. So, if we are now looking at a plane D 1 2, the corresponding reciprocal lattice vector will be, now we have to look for 1 2, that is 1 intersection along A, 1 along A and 2 along B. Now, this what this represents is the reciprocal point, that is D star 1 2. If this is D 1 2, we represent this as D star 1 2. So, this therefore, now defines the diffraction pattern, it also defines the reciprocal space. So, if you sit down and study this diagram a little carefully, you will definitely see that the 1 to 1 relationship between the direct space and the reciprocal space, and that 1 to 1 relationship will therefore tell us that if this is a lattice, if this is the red one is a lattice, then the collection of all these blue dots should also be a lattice, and therefore, this we call as the direct lattice. This now becomes the so called reciprocal lattice. So, in the reciprocal lattice, we have two vectors A star and B star with an angle of gamma star defining this particular nature of this lattice. So, the distribution of the diffraction spots therefore, should come at these blue points. So, keeping this in mind, we will see how we can use this idea of reciprocal lattice, because we always see the reciprocal lattice in an experiment. So, when we do the experiment, we put an X-ray, we send an X-ray beam onto the crystal, a collimated X-ray beam onto the crystal. The crystal now diffracts, so it will follow the Bragg's law, and therefore, we have an incident ray and a diffracted ray according to the Bragg's law satisfaction 2d sin theta lambda, and therefore, we will get to positions which are now the reciprocal lattice positions, and therefore, we will get spots. Now, these spots which we will get in a single crystal are therefore, each and every spot now is a representation of a plane in the Dirac space. So, every plane in the Dirac space gets represented by a point in the reciprocal space, and this is a very big advantage, because we do not have to look at the plane, we look at only the reciprocal lattice point. We also know another factor, that every plane therefore, if any atoms lie on that particular plane, they will all correspond to the same phase, and therefore, when we get this reciprocal lattice point, let us say 2 1 here, 2 1 will contain information of all the atoms in that particular plane in the Dirac lattice, and therefore, 2 1 is something which is once we get the coordinates of 2 1, it is important to see what is the intensity that is associated with 2 1. So, before we go to the analysis of the intensity, we have to do one other way in which we can look at the Bragg's law. Whatever Bragg's law we derived earlier is in the Dirac space. We took the parallel planes, we did the construction, we found the phase angle and so on, and showed it is 2d sin theta equals lambda or n lambda, where n is the order of the reflection. On the other hand, when we do a diffraction experiment, what we see is the reciprocal lattice image. That means, we see the spots. So, it is always good to see whether we can actually think of deriving the Bragg's law in that space itself. So, in other words, can we have a Bragg's law in reciprocal space? Can we derive Bragg's law in reciprocal space? This was the thought process which was put to develop what is known as the Ewald construction. So, it was developed by a person by name Ewald. So, it is known as the Ewald construction. You can directly visualize the diffraction conditions by means of which reciprocal lattice points come, and that is how it is done, which is shown in the next view graph. Here you see something which we have to do a construction. What you see are the points here which are the reciprocal lattice points. So, I have drawn the reciprocal lattice. So, the reciprocal lattice is similar to the reciprocal lattice shown here. So, all these points which come, we know now how they are coming, and knowing that how they are coming, we have taken these points and we have transferred it onto the plane. Now, therefore, this is now a planar representation of the reciprocal lattice points. Then what we do is we do what is known as an Ewald construction. So, each plane is a reciprocal lattice point, as we saw just now. So, what we do is we just take a circle, we draw a circle of radius 1 divided by lambda. Lambda is the wavelength. Remember that the reciprocal lattice is represented in inverse of length, the dimensions of inverse of length. So, we therefore take a circle and draw the circle of radius 1 divided by lambda. That particular circle we can draw with some center here, and you see that this is the circle which we have drawn. This is a circle drawn with the radius 1 divided by lambda. So, if you consider the center as here, this to this distance or that to that distance is 1 divided by lambda. Now, we define on this particular circle, this circle can be anywhere, okay. It can be anywhere in the 2 dimensional space we have drawn here. It is 3 dimensional because we are now going to eventually change the circle into a sphere, but at this moment this is a 2 dimensional diagram, and so we have a circle. Now, this circle can be drawn anywhere, but it should have a diameter of 2 by lambda or a radius of 1 by lambda. So, this radius of 1 by lambda is with respect to some origin. So, we take this one of the reciprocal lattice points to be an origin. So, if we take this as an origin of the reciprocal lattice point 0 0, now this is the circle with a 1 by lambda radius which is drawn in such a way that the circle passes through our 0 0. So, remember the circle is passing through our 0 0 on the circumference. So, this is the circumference of our 1 by lambda sphere. So, there is a center up here. Now, let us say we send an X-ray beam from the top. The X-ray beam from the top now comes and falls on this particular origin, which is a reciprocal lattice point. So, it scatters. Now, what it therefore tells us is that any point which intersects with the circumference of this circle, because we said the circle is arbitrary, it can be put anywhere. So, any point which intersects with the surface of this particular circle will give us therefore the diffraction condition that is satisfied. So, can we use this method to find out what is the diffraction condition that has to be satisfied. So, therefore, we see here in this particular example we have taken the reciprocal lattice points, and we see that this is the vector b 1, the reciprocal lattice vector, and this is the vector b 2, which is the second vector. So, b 1 and b 2 now represent the reciprocal lattice vectors, reciprocal lattice dimensions. So, b 1 and b 2 are the reciprocal lattice cell dimensions or reciprocal cell dimensions. So, having seen b 1 b 2 being representing, this is let us say one direction, this is the other direction. You see we go up in this direction drawing these points, and these are all the points which are lying with the origin here, and these are all the points which lie with the origin with respect to the b 2. So, we have a b 1 here and a b 2 that is defined. So, this is the origin. Now, you see in the diagram which I have drawn, it so happens that the point which is now 2 along one along the one direction, that is this point, this is the, if you consider b 1, and this is the point 1 along the b direction. So, we see that this coordinate therefore, which lies on this is 2, this is 1 in this case of b 1, and b 2 is 1 and 2. So, there are 2, this is the second position. That means, this vector h is represented by 1 comma 2. So, since this vector is, this is the crystallographic direction in some sense. So, this is 1 comma 2. So, the diffracted beam is now shown as S in that direction. So, therefore, what happens is, this is the incident beam, this is the diffracted beam. You remember the diagram which we drew, the diagram will be, this will be the angle 2 theta between the incident beam and the diffracted beam. Now, if you take the bisector of that, we already know that should be the direction of what we call as the scattering vector. So, this is written as the trace of plane normal to h. So, this will be the direction of the scattering vector. So, we therefore have a theta here and a theta there, and this is the center of the circle, and we have the incident beam and the diffracted beam. Now, what happens is that as you see here, there are several reciprocal lattice points which on this grid, but none of them are intersected except the one which you have taken as an example. The reason is obvious, because we are keeping the reciprocal lattice fixed. That means, we are keeping the crystal in one position and then sending in the X-ray beam. So, if we keep crystal in one position and then send an X-ray beam, very often than not there may be no diffraction coming, no reflections are observed, or we may observe a reflection by chance like what we have seen here, and we will see this particular reflection. We do not see any other reflection. That means to say that whenever the reciprocal lattice intersects with the Ewald sphere on the surface, now instead of the circle I am going to call it a sphere, because we are now going into 3 dimensions. So, we call it as the Ewald sphere. So, anyway, any time an Ewald sphere intersects with a reciprocal lattice point, the surface of the Ewald sphere, then we get the diffraction condition satisfied, and this diffraction condition is satisfied if h lies on the surface. And if h lies on the surface of this sphere, then the scattering angle we know it depends on the length of h, the Laue condition, the length of h, s minus s naught by lambda. So, the length of h therefore is equal to 2 sin theta by lambda in magnitude. We have shown this magnitude of h is 2 sin theta by lambda. So, it is 2 sin theta by lambda. Now, what is 2 sin theta by lambda? It is 1 over d of h k. So, therefore, you equate these two, you will get the Bragg's law, 2d sin theta equals lambda. So, therefore, the Ewald sphere has a radius of 1 divided by lambda. So, what is the catch here? The catch here is the following, that we have kept the crystal in a single position, sent in the X-ray beam. By chance it so happens that in this diagram which we have shown purposely, there is a point which intersects with the surface of the Ewald circle or the Ewald sphere, and therefore, it satisfies the Bragg condition. So, in order to satisfy the Bragg condition, we have to have this equation satisfied. That is because of the fact that the vector h, which is the reciprocal lattice vector, should have a magnitude which is equal to 2 sin theta by lambda. Then and only then we get diffraction. So, we see here that in this entire diagram we have shown only one possibility of a diffraction point. Then how do we get all these reciprocal lattice points to diffract? The solution is very simple, you rotate the crystal. Now, as you rotate the crystal, this reciprocal lattice itself will start rotating. So, as the reciprocal lattice rotates, different points in the reciprocal lattice can come and intersect with the evolved sphere here, the surface of the evolved sphere. So, as and when any of these points, for example, here there is a near intersection, it may slightly turn around and then the next point will be intersecting here. This will intersect and like that. So, all these points will start intersecting. Now, what is the limiting condition for that? The limiting condition is that now this becomes the radius, 2 by lambda becomes the radius, and therefore, this circle which we have drawn outside, or the sphere which we can draw outside in 3 dimensions, which is referred to as the limiting sphere. So, this has a radius of 2 divided by lambda, and this 2 divided by lambda is now the limitation. So, all those reciprocal lattice points which lie within the 2 divided by lambda have a chance to intersect with the evolved sphere, which has a radius of 1 divided by lambda. So, the radius of the limiting sphere is 2 divided by lambda. So, the reciprocal lattice points which lie within that particular sphere have a chance when the rotation takes place, the 360 rotation of the crystal will bring all these points which are shown within the limiting sphere to intersect with the evolved sphere. And whenever there is an intersection with the evolved sphere, you get diffraction. So, it may so happen that as you rotate the crystal, there may be positions of more than 3 or 4 reflections satisfying the Bragg's condition. Then you, at that particular angle of rotation of the crystal, you will get more than one reflection. So, it is not necessary that one at a time should come, you can get any number of reflections at a given angle theta in different directions. See, the directions are different, this point and let us say this point were to intersect, we will get one diffraction in this direction, another diffraction in that direction, and so on. So, it goes in that particular fashion. So, what we therefore do is to see that this set of points which will now present or which are present in the limiting sphere will have a chance to intersect with the evolved sphere. And this is a point which therefore allows us to look at Bragg's law in reciprocal space. So, we now know under what conditions and under what circumstances a crystal can give diffraction. So, we have a crystal, we get the diffraction spots, and these diffraction spots will follow this particular equation, which is the Bragg's equation. So, I think at this level we have now just understood the Bragg's law both in the direct space as well as in the reciprocal space.